Yeah. Yeah. I can post you the MAT one. Similar. What? Sabah. You ask the student understand or not? Okay. Okay or not? Any more question? Okay. Hello, hello. Okay. Okay. So okay. So okay, so part B here. Okay, part B here. How to compute the line integral? How to compute the line integral of a vector, conservative vector field in particular? Do dot product. Okay. But in this case here, what is my f? My f, yeah, is this thing here, but in particular it is conservative. So I can write it as a del of, yeah. So del of a little f. So we can use the FTC. Okay. So we can use FTC. So what's FTC here? So what's my f? Yeah, so my f is here. So let's get it out. F power 2. Okay. So the capital F in this case here is the gradient of the f here. Okay, which is the gradient of the function we found. Okay. So how to apply FTC? No more integration, just substitution. Substitute what? Okay, substitute the endpoint, the terminal point into my little f minus, okay, minus the function evaluated at the starting point. Okay or not? Yeah. Okay. But how? Here is xy or here is pi t or so how to get xy? Huh? Yeah. Right. So you get from the curve equation here. Okay. So you get from the curve equation. So when the curve at pi, what happened to my xy? Yeah. So what's that? E pi sine pi and e pi cos pi. What is that? What's this? 0 and cos pi is what? Negative. So negative e pi. Okay. How about r and 0? 0 and 1. 1. Because e to a 0. Yeah, e to a 0 is 1. Okay. So the starting point, the end point is 0 minus e to pi. And then the starting point is 0, 1. Okay. Okay. So you sub your point into our f. Okay. So into our f, what do you think we get here? Anyone finish computed? Yes. E to the 6 pi minus 1. Okay. So you sub the xy into the function, sub xy to the function, and then take the difference. Try and compute. Yeah. See if you get 6, 4 to the 6 pi minus 1. Any question? Question. So let me write down what we use. So the second step here. So the second step here, we use FTC for line theorem. Here we check curve. Okay, so check. Okay, and the first step here is because F is conservative. What? Okay. Huh? Question. Continue. Okay, happy. Okay. How about the rest? Which one? Question? Which one? Oh. Of conservative. So the proof of conservative, I just use theorem. Okay. Proofs of 是以先还是以先? Yeah, proof of conservative, we just use theorem. Yeah, we just use this equation here. Okay. Yeah. Okay, so before we end, I will take a break. Another break. Okay. So for this 3 variable case, I just leave you to do it. Is it okay? So you need to check for 3 conditions here. Okay. So why is it called conservative vector field? Okay. So typically we have a vector field from potential energy. Okay, if you consider potential energy as a scalar field, we will have this potential energy. Okay, but this vector field, right, will satisfy conservation of energy. So what does it mean? For example, you throw a ball. Okay, you throw a ball. Okay, start with a low potential energy. You throw it up, so your kinetic energy decrease until you stop. Okay, turn to potential energy, but due to gravity, the potential energy become kinetic energy again, and then drop until potential energy. But this energy have to be conserved. What do you mean by? Yeah, okay. So you conserve the energy under the force field. Okay, under the gravitational field. So that's why we call this field. If we can write it as a, you see, can see here. So if we can write it as a gradient of some scalar field, then they have to satisfy the conservation of energy. Then we call it the conservative force field. Okay. Any question? Any question before we take a break? No. Okay. Later after the break, we will talk about Green's theorem. Okay. Green's theorem.
就是它的名词我就是不太清楚这个那个 FTP 是什么意思
？FTC Fundamental Theorem of Calculus Theorem of Calculus。
然后这个 conservation 就是它是表示什么意思？
什么意思？
就是 conservation
？conservation 就是中文没有 conservation 就是
因为我知道它中文什么意思，但是能不能形象地说一下，就它求出来是具有什么样的特征，是要
它的特征就是如果你考虑它的 energy 的话，energy 的转换
，between 之前没有讲 energy 的时候，
没有，
谈到那个 conservation，所以说
对，
可以从纯数学角度来理解这个 conservation。
不能，因为它这个字就是从 physics 过来的。
哦，对，那
它只是一个，如果数学上我就是把它写成 gradient 吧。
但是你这个概念不仅仅是谈论到这个 energy 的时候才可以说吧？你就是
其他 physics 的我不确定。
OK，那你就是在 energy 的时候，你能不能说一下这个 conservation 它就有什么特征？
特征就是如果你看，如果你这个东西是被这个 force 移动嘛，对不对？
是。
然后这个 force 什么情况呢？它要符合，它要符合这两个条件，就是就是你可以从 potential energy 得到这个
F。potential 就是它的梯度嘛。
我不知道中文是什么就是那个 potential 它的位置的那个 energy， 我不知道中文是什么。
哦，势能。
势能 ，OK，就是用它，如果你找它的 gradient，你就会找到这个 F。And then 这个 F 呢，也可以是从这个acceleration 来的。
F 是 force 吗？
是 continuous force field 是。
但那个 potential 势能它是标量，但
是你取了 gradient 过后，你会拿到 force，它是这么说。
哦，势能取标量之后，它大小就等于那个 force 是吗？就大小上就是取。
都是大小，因为我取的是 gradient 嘛。
对 gradient，
所以会有 vector 出来。
但是我记得那个 potential 它是个标量，它不是个质量，就是
potential 是一个向量啊。
potential 是那应该不是势能意思。
没有 ，P 是一个势能，势能的意思是说，我给你一个点，你告诉我它多大嘛，所以是一个 RNT。
势能，你定义势能的时候，你要先确定一个零，就是零势能面，然后你才能确定它势能。
因为没有，所以 energy 是一个方程，从哪里去哪里先？
能量。
可是我要点名一下，让我点名一下。连上次是手。OK，C 乘少飞 not here， 方舟 here， 子涛 not here， 高启晓 not here， 宏宇 not here， 李杰 OK， 李培 OK， 李玉章，连夜 OK， 天阳 here， 佳琪 OK， 品义 here， 夏红 喂，夏红，凌波 OK， 凌波 not here right， 香鱼 also not here， 香鱼 not here， 玉林 OK， 杰森是杰森 OK， 金花 here， 子飞 裴武没有上课休息啊，裴武 Where's 裴武 not here， 西龙 not here， 王 OK， 吴星宇 here， 谢宇轩 I think here， 你是什么？裴武，你看没有看到你的？裴武 OK， 李杰 OK， 李培 OK， 子凯，景荣 I think I saw 景荣 OK。景荣 Did you receive my message or not？ You submitted the wrong quiz. I think you submitted the wrong quiz. You submit the wrong quiz PDF. Wrong. I sent you a team message already. Team message. Zhang Yun. Yeah, Zhang Yun, right? Zhao Jinghan. Zhao Yixian. Yixian.子康。嘉璇导演。Daniel here, Berwin here,定义 here, 嘉明 here, 水龙、佩瑜、宋豪、宜迅、邱生、管天、明、袁耀、文达、宜辉 here, 宜顺 what? 听下，宜顺啊，伟兰，宜顺，洪明、嘉盛、Renis、伟 King、韦涛、青柔都 here 啊，宜昭、泽义、热真 ，OK， 凯杰，丛凯杰，you submitted your quiz yet? You submitted. 雅美，浩伟，泽辉 ，OK， 柯子正有福于吴承泽，
OK， 老师我查过这个 potential 的话，它不是势能意思，它是电势，就是电势确实是个矢量，对，是个 vector， 对，它不是势能，我查过，对。
没有吧？它应该是个，
它就是怎么说？就是它好像不是 vector， 对，它不是
vector， 它是一个 RNGR，
它记录了那个，就是它那个电势能的那种大小。哎，我也很难表达，就是我不知道它什么意思。对，就比如说你通过两个做，就是它就能衡量他们之间做的功，就类似那种感觉。对，然后你们就是说一下这个 conservative， 就是对它的这个是什么意思？
就是说，它的总体，它一开始的时候，你一个东西一定有 potential energy 跟 kinetic energy 嘛。然后到它结束的 potential kinetic energy， 那两个加起来一定要一样。不是这两个加起来一样，就是下面加起来跟上面加起来一样。就是东西丢上去嘛，它有一个 kinetic energy 上去过后，它全部变成 potential energy 了。
我懂。然后那个就是老师，还有那个 scalar field 就是它就是
RNGR 的一个方式，
什么
RNGR 的一个方式。
对，就它具有什么特征？就是叫它 scalar field，
没有特征呀，没有特征。再给我讲一个东西啊，
就是它，我们开始。然后我问个就是
，OK，
scalar field 就是你 potential 一样的时候，它那个是不是 force 就一样，就是这个道理。
不一定，就是在每个点位有
不是 force， 我指的是大小，不是指法。
对，大小不一定一样，
大小也不一样。
OK， 给一个 example。好了 ，testing。Okay, let's start again. So because just now I didn't record, right? So maybe I will post the MNT version 1 into your class. Okay, so I think a lot of you confused when I talk about vector field and scalar field. Okay. So what is scalar field and getter field? Okay. So for example, vector field on R2. Okay. Scalar field on R2. Okay. So maybe give an example. So I'll give an example. Okay. So sophisticated one. So for example, this one I just put xy. Is that rainy, son? Rainy, yeah. Hello. Long time no see. Okay. So for example, gxy equals to x plus y. Okay. So what's the difference between vector field and scalar field? Because this word come from physics. Okay, this word come from physics. So there's physics interpretation here. So for example, what's the vector field? Meaning on the point, every point in R2, I got a vector. Okay, I got a vector. For example, what? For example, at 1, 1, okay, I got a vector 1, 1. Okay, and then here, maybe, so here is a 1, 1. Maybe here is a 1 minus 1. Yeah, so we got a vector here. And then here, so maybe I use another color. Yeah, I got a vector here. I got a vector here. And then here is a minus 1, 1. Here's a minus 1, minus 1. So we got a vector here. Okay. So at every point, we have a vector. Okay. So we have a vector at every point. Okay. So what's the vector at 0 in this case? Is the 0 vector. Okay. So this is a vector in every point. Okay. How about scalar field? Why we call it a scalar field? No, because on the point, I only got a number. Yeah, I only got a value. For example, at 1, 1, I get 2. Okay. Here we got 0. Here we got minus 2. Here we got 0. And so on. Okay. Above the point, I only get a value. Okay. So for example, this is 1, 1. So this is 1 minus 1. So this is minus 1 minus 1. And then this is minus 1, 1. Okay. For example, if I pick 2, 2, what's the value on 2, 2? 4. Okay. So every point, I stick a number on it. Vector field, every point, I stick a vector on it. Okay. So the field here referring to the domain. Okay. Like you're standing outside the field. Yeah. So let's say my function here is 0. That means what? Every point I attach a 0. Okay, every point I attach a 0. Let's say I define this scalar field to be 0. So every point I attach a 0 value. Not distance, this is the function. It just means that you take any points, you just get 0. If I define my scalar field to be 0. Okay, so this one is an example. Okay, so my main point is vector field. Every point in the domain you attach a vector. Scalar field. Every point in the domain you attach a number. If you go and look for this video, right, physics video, you will see something like this. In the domain, they attach vector. In the domain, they attach value. I forgot, but yeah, you can try and have a look. Okay. Next. So Green's theorem. So before talking about this Green theorems, right, we still need to deal with this orientation here. So the positive orientation here of a single closed curve refer to a single counterclockwise traversal of C. So when we say positive orientation, it usually means anti-clockwise, right? So this is how we draw our XY plane. Okay, why our XY plane doesn't draw like X go to the right and then Y go to the bottom? Why? Because we have the orientation. We have to add anti-clockwise. Okay, this is a positive orientation. Okay, so if you go further X, Y, Z, you use the right hand grid rule. Yeah, so these are all positive orientation. Okay, so how about negative orientation? So you need to go clockwise. Okay, negative orientation, you go clockwise. Okay, positive orientation, you go anti-clockwise. Yeah. Okay. Yeah, so this is the orientation. So what's Green's theorem? Let's see. Okay, we have a positive oriented piecewise smooth simple close. Okay, that forms the boundary of a region D. Okay, so it cuts out a region D. Okay, in XY plane. Then, if so positive oriented, so meaning anti-clockwise, piecewise smooth, just smooth. Okay, piecewise smooth. Maybe have some non-differentiable point, a few different non-differentiable point. That's fine. Piecewise smooth, single close. Okay, close is what? End point and starting point is the same. Okay, so it's a loop. Simple meaning it doesn't self-intercept. Okay, that's all. Okay, it forms a boundary of region D. So if you are loop, you bound a boundary inside, right? So you got a. So the simplest example here is the circle. Okay, so circle bound this. Okay, so this is D. So if P and Q has continuous partial derivative on the open region that contain D, then what happens here? We relate multiple integral to a line integral. Okay, so we relate multiple integral to line integral. So what does this mean here? So we have a C. So for example, this is a perfectly piecewise smooth. Okay, this is piecewise smooth. This is simple, close. Okay, you need positive orientation. So just add a orientation on it, positive. Okay, and then it bound the region D. Okay, bound region D. Okay, so what is going on? So the multiple integral is equal to the line integral. Okay, so multiple integral of what? Okay, of what? Of del Q over del X minus del P over del Y. Okay, at the moment here, P and Q can swap, right? Doesn't matter. However, on the right hand side, you can see that P start with dx, Q start with dy. Okay, so if P start with dx, so you need to differentiate with respect to y on the other side. Q start with dy, you need to differentiate with respect to x on the other side. Okay, and then you need to introduce a minus sign in front of the del y component. Okay or not? Okay, so not okay. Okay, so so let's read from left hand side. Okay, so typically, let's say we start with left hand side. We have integrate line integral of p dx plus q dy. Okay, so what's on the left hand side here? You can change this line integral into a surface integral. Okay, or the multiple integral on the domain bounded by C. Okay, let's call it D. Question? No? Okay. So far okay, huh? So far okay. So we go from a line to a surface bounded by the line. So far okay or not? Not okay. Okay. But what's the function we integrate over? Okay. We need to differentiate the dy function with respect to x. You see? So q is with dy, but right? But we differentiate with respect to x here. Can or not? And then take away differentiating the x function with respect to y. We swap the order. Can or not? Can or not? Song Hao. Yeah, what's the problem? Huh? Okay, so there are few things to note here. Okay, few things to note here. So here is a line integral. Okay, okay. We are relating line integral with double integral. How about the domain? The domain here is a boundary. Uh-oh. Hello. Okay, so hello. Okay, come back. Okay, so the domain here is a closed curve. Okay, so closed curve bound a region. Okay, region bound by closed curve. Hey, hello, wait, come back. Okay, so you relate a double integral to a line integral. Okay, so what happened to the function inside? Okay, what happened to the function inside? So your line integral must start with this kind of specific function, p dx plus q dy. Have you seen this kind of form before? P dx q dy. What is that? What is that? What's that? The word done. Right? Word done we can split into dx, dy, dz. Okay? So you can think of this p and q coming from the vector field. Okay, okay, but the function on the left is what? It's a specific one. Okay, you need to differentiate the second function with respect to x minus differentiate the first function with respect to y. Question? Where your p and y? Where your p and q come from? I thought I said this now. Okay, it's okay. So, so one typical situation you will get is from here. Okay. So we just now we said that this one can split into f1 dx plus f2 dy. Okay, so you see, so this here is an example of this case. P dx plus q dy. Here is f1 dx plus f2 dy. That's it. Can, both can. If you realize that the double integral inside your double integral, okay, the difference there is coming from some other function, then you can rewrite to the left hand, right hand side. Del q del y minus cannot. Unless on the other side you also change the order. Yeah. So this order is fixed. Okay, the order of this is fixed. So that have to be 3x, y, 3y. No. You see, x for the function of x, you differentiate with respect to y. For the function on y, you differentiate with respect to x. So it's opposite. Okay, and then you take minus on the derivative with respect to y. Yeah. So there's sign different there, and then the order you take the differential. You need to take note. Okay or not? Okay. I mean, you don't know why is it true. This is just a way to compute. Okay. Because we don't prove it, so we don't know. Okay. Okay. Okay, next. We can rewrite this line integral into this sign here. So integral with a circle or a loop. Okay. If we write this, this means that the C we integrate is a closed loop and also it is positive oriented. Okay, both positive oriented and closed. Right. because closed line is a loop, so I can draw a circle there. Okay, if I put circle here, it's also a line integral. Or we can use another notation. We can write del D. Okay, what is del D? D is a region, and then we can find the boundary. Okay, del D. Integrate over the boundary. So in this case here, so remember this example here. Okay, what's the boundary of this? It is C. Okay, C is equal to the boundary of my this. Yeah. Okay. These are just notation. Okay. Ready to go to example or not? We'll do a few examples. Huh? Yeah, do example. Okay. Yeah. So for now, you don't need to understand first. You just need to listen. Understand the instruction first. Okay. No need to internalize first, but instruction. Okay. Now, what do we do? So we have a boundary of the triangle. Okay. Connecting 0, 0, 1, 2, and 0, 2. Right? And then we want to do line integral over this function here, 4x squared y dx plus 2y dy. Okay. So I put a circle here. What does it mean? If I put a circle on the line integral, it is a close. Okay, close move, positive oriented. Okay, good. So positive oriented, piecewise move. Okay, positive oriented meaning we go from 0, 0 to 1, 2 to 0, 2, and then go back to 0, 0. Okay. So line integral, how to find line integral? Again, line integral, how to find? You need to P pair. Right, sure, that one is green. I haven't used green first. I want to do original. Original recipe is what? Reparameterize the curve. Okay, reparameterize the curve. Okay. So how many curves here? So we split this into 3 curves, C1, C2, and C3. Okay, C1, C2, and C3. So C1 is what? Y equals to 2x and y equals to 2x. The gradient is 2. Right. If y equals to x, the point should be 1, 1. Okay. Y equals to 2x, what happened to x? X is just x. Are you guys confused or not? Let us put t lah. Don't confuse ourselves. Okay. T is going from where to where? Zero to 2. Good. How about C2? 0 to 1. Wait, 0 to 1, huh? Don't cheat me, eh? 0 to 1. I thought I'm going to test you, you test me. Okay, what is C2? What is C2? What is C2? Y equals to 2. X equals to? S equals to T. Okay, T going from where to where? 0 to 1. Hey, careful, the orientation going from where to where? Huh? 1 to 2. 1 to 0. Okay, so we change the orientation. 1 to 0. Otherwise, we need to introduce the sign. So we should better change it first. C3, vertical curve. S equals 0, Y equals to T. Okay, T going from where to where? 2 to 0. Okay, good. All right, so we got all these. So we need to put into the line integral. Okay, so we split our line integral into 3 parts. So C1, C2, and C3. Okay. So on C1, what happened? It is going from 0 to 1. Okay, 4 times 1. becomes t, so t squared. Y becomes 2t. But you need a derivative of x with respect to t, right? So it's 1. So you multiply by 1 here, dt. Okay, plus 2y. Y is 2t. But you need to multiply by the y derivative, right? Which is 2 dy. Yeah. So we put few things together. So if you want me to remind you, so here, what is integrate a line integral with respect to a specific direction? So this is just replacing f with respect to t of x prime t dt. Okay, so this is the line integral with respect to x. Okay, you will have a contribution. Okay, you will have a contribution from your tangent vector. Yeah, dt. Correct. This is dt. All of them are like that. Okay, cannot. Okay. Okay or not? Does everyone get this line? Yeah. 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 Can get this line? Everyone can get this line? Do you know how every factor coming in here? Okay. So you can do it for C2, C3 also. Okay, so let's do it. For all the C. Okay, what's the factor here? X prime t is 1, y prime t is 0. So here is 1 dt plus 2y, 2 times 2, y prime t is 0. Okay, and then, yeah, and then the third one is 4 times 0 squared times y times y is s prime t in the case. You get 0, y prime t you get 1. So here you put 0. And the other one, 2 times t times 1. Make sense? Okay, so compute this. Let's see what do you get. Yishun, what do you get? Negative. Okay, so it's negative 2 over 6, 2 over 3. Yeah. So it's 6 minus 8 over 3 minus 4. Okay? No, you take your time. You take your time. Yeah. Yeah, you take your time. Okay? So you see how many components we need? We need to substitute our function with respect to the parametric curve, and then there's a contribution from the derivative of our curve, right? Okay, and then the domain, the range, the integration domain, range of integration domain. Ija, don't want to calculate. Okay, any questions? Sorry? What? 40 square, yeah. 40 square. 40 square. Okay, okay or not? Okay, okay. So next, We want to use Green's theorem to check it. Okay, use Green's theorem. So why can we use Green's theorem? Because this is a closed curve. Simple, closed, piecewise smooth, positively oriented. Okay, so it bound this circle here. So okay, so how we turn this into a Green theorems? So let me write. Wait, so let's compute. Let's write down this line integral here. So it is 4x squared y dx plus 2y dy. Okay. So how to write this as a double integral? Okay, let's call this region D. Okay, call the region D the triangle. Call it D. Okay. So what's the procedure? Okay, you need to take the one on dy. Okay, differentiate with respect to x or y. X opposite, right? Okay, and then minus the one that come from dx. Okay, and then differentiate with respect to y. Okay, opposite one. And then this one is dn. And dn. So in this case here, our p, let me write down. My p here is 4x squared y. My q here is 2y. Okay, so just differentiate it. So this step is by Green's theorem. So differentiate with respect to x of 2y, you get 0. And then the second one, you get 8x dA. Okay. Sorry, something wrong. 4x squared. Okay, 4x.
differential y.
Like a boss, make you come here do Like, come do double integral. How to do double integral? Yeah, fix. Okay, what theorem? Fubini's. Okay, Fubini's theorem. So you do dx dy or dy dx? Dy dx, Okay, we fix dy dx, I have to cut again. Correct. Very good. Dy dx. So x is going from where to where? X going from where to where? 0 to 1. Okay, good. X 0 to 1. Okay. So you see, x is going from 0 to 1. Okay. What happened to y? Okay, you can see that when you fix an x, the y is like keep reducing. Okay. No, bounded below by what? 2x. Bounded above by 2. Okay. So bounded below by 2x, bounded above by. Okay, so this is the double integral 0 to 1. Wait, don't fight. Don't fight, Don't fight, Don't fight, Okay. Yeah, you use dx, dy also can. Okay. Okay, so what's the answer here? Sorry, negative. Yeah, so what's the answer here? Negative is coming from the derivative above. Yeah, the special one. Correct. Okay, so what's this answer here? Yixin, got it or not? Hey, how can it be different? Shouldn't be different, right? Otherwise, the theorem is wrong.
Sorry.
Yeah. If it's different, then you found the counter example to the theorem. What's the answer? Why no battery? Oh. Isa, what's the answer? What's the answer? Yeah, sure. What is this answer? Yeah, so it's the exactly same answer, -2/3. Okay. Is it? Yeah, I mean depends on. Sometimes maybe surface integral is harder, so you can do line integral. Sometimes line integral is harder, you can do surface integral. Okay, so you can go between these two. Is that okay? Okay. Check the second last step, is it okay or not? Okay, so not yet. Not yet. Not yet. Okay. Okay, maybe let's do this example quick. So this example very quick. Use both. Use both. Let's use the greens first. Okay, use green first. Okay. So to use green, right? So this is a line integral of a circle. Okay, a circle. Circle with radius what? 3. So center at 0, 0. Okay, good. Okay, so if yeah, a bit advanced. Wait first. Wait. Can I change the polar coordinate also? Can. 反正你等一下了咯，不一定。Okay. So if we're gonna to use Green's theorem, what's the surface that bound by the circle? What's the surface bounded by a circle? It's the this. Okay, it's the this. Okay, it's the this, not donut. It's the this. Okay. Okay, so. Okay, continue. So we change C into line integral on C to a surface integral on D. Okay, because it's an open this already. Okay, what happened to the function? You need to take the function on dy, differentiate with respect to what? X. Okay. Minus the function from dy, integrate from, differentiate from with respect to y. Or what do you get? D. So you just get 7 minus 3. Okay. So you see, so fancy one, this function only left with 7 minus 3. Okay. Minus 3, sorry. Minus 3. Okay. So what is this? 4 times the double integral on function 1. What is this? Area of the area of this circle don't have area. Area of this. Area of this is what? 4 is pi r squared. Okay. Pi 3 squared, which is 36 pi. Okay. So let's say Ho Ming say one. Ho Ming say try direct method. Okay, wait. Okay, so how you parameterize the curve? Polar coordinate, right? Your chance, polar coordinate. Right? How's the polar coordinate? Yeah, so what's the vector function? What's the vector function here? radius is 3. 3 cos theta and 3 sin theta. Okay. So the whole 0 is going from 0 to 2 pi. Okay. So what is r prime t in this case? Minus 3 sin t and 3 cos t. Okay. So now we do line integral. Okay, so how to do? Or we already parameterize our line, so we need to do our line integral here. Okay, so let me write. Okay, so our f is what? Okay, our f is, yeah, let me write it as y plus. Our f here is what? Is 3y minus e sine x, comma 7x plus square root y to the power 4 plus 1. Okay, so this is our f. And then we need to substitute the curve inside the curve. Okay. So we'll get some very looks complicated function. Sine of 3 sine t. Okay. So 7 times 3 cos t plus square root of 3. Can we just write it down and then we skip?
Okay. So you call homing, complete this, and then later you call it a Buddha.
Yes, right. This will complete the graph and then show us the step. Okay, you go back. Where sine t? Yeah. Here is x. Here is x is correct. So y to the power 4. Y is 3 sine t. And then x is 3 cos t. So here is cos t. Right? Okay, sin sine t. Yeah. Sine times sine 3t, right? So sine times sine 3. Okay. Now okay. Okay, yeah. Okay. So just to be complete, we write down the final form and then we will pass it to Hongming.
This question will be solved. It will be
你要做，你刚才自己讲啊，你可以这样子啊。
给老师的建议，是老师也给你建议做。朋友都在帮你啊，我都帮你。
Okay, so you need to dot product the two vectors together. Okay, so the first vector is this f. Okay. Maybe I make this smaller. Okay, and then this one dot with the vector of my curves. Yeah, x prime t is the tangent vector of my curve. Yeah. Okay, so you dot these two together, expand it, and then do the calculation. You will get 113.07097. I don't know. I just saw the answer.
Textbook also use this method, do you?
Don't know previous one. Okay, so how many? Please write down the step for us.
Yeah, I write according to that.
And it's easy, very easy. You see, what is this? This is just sine t, right? Sine t. So multiply together, you just get sine square. You can use double angle here. But how about this one? Sine t, sine something something. That one you can use integration by substitution. Use substitution. Integration by substitution. You see, cos t, you substitute sine t, drop out, so we'll cancel out. So use substitution. Okay. And then cos t, and then you say my lecturer asked me to show this.
No, dude.
Okay.
If I didn't compute this, he don't let me take final exam.
Yeah, final exam.
Hey, what? You guys want to left already? Huh? 10 minutes left. Huh? After everything, I will say. After everything, I will say. Yeah.
你那叫 broad 嘞。
Bro, what?
你不要讲每一个都会考的，你要 specific 哦。也不要像
Okay, okay. Okay, okay. Before we leave, so Monday I already booked the room. Okay, A4G09. Okay, 12 o'clock to 3. Okay, A4G09. Yeah.
12 o'clock 啊。
Yeah, 12 to 3. So if you cannot make it, we will record.
Remember the report.
Okay, we will record.
A4.
A4G09, the usual one.
所以有人打包多少？也可以哦。
Okay. Yeah.
还有个 IA 不一样，他的不一定有钱。
等下要出去吃嘛？我要搬家。
麻烦现在睡一次啊。
这样啊？
要这样子。
还是治疗再回来搬？